Then why we have to reduce the variance? Then please refer to our SGD course, where the variance was the main bottleneck for our performance. Because of the variance on your gradient estimation, we cannot converge to the optimal solution if we keep the same step size all the time. And the variance of your stochastic gradient always there. That always makes some error, even if you run infinite number of iterations. Okay, so if we can reduce the variance to 0, then we can converge to the optimal solution even with constant step size with stochastic gradient descent algorithm. And the constant step size, the good side of constant step size was the conversion speed. Okay, the conversion speed looks like this: 1 minus, so that was like beta over alpha. No. Alpha over beta, number of iteration, times some constant plus sigma square. So the SVRG is invented to reduce this sigma square part so that you can utilize this part, and also you can remove this part as well. So you can very fastly convert to the optimal solution even with the noise gradient descent, the stochastic gradient descent. So how can achieve the zero variance in the end? The idea is this. So basically in the paper, SVRG paper, we consider this kind of objective function, the sum of functions where fi is beta smooth and f is alpha strongly convex. So each fi satisfies beta smoothness property, and the total objective function satisfy alpha strongly convex property. Okay, and the algorithm is, actually we already discussed what is SVRG in our course. So for s from 1 to the end of time, we update x tilde, which is equal to x tilde s minus 1 at the beginning of the s times log, and we compute the mu tilde. This is the full batch gradient. So consider all function fi and then take the gradient at point x tilde. Okay, and then set x0 is equal to x tilde, and then update x0 using m iteration. Simple SGD we use for this process. So every time randomly pick one index. Let's say this is it. Of course, it belongs to 1 to an integer value. And xt plus 1, the starting point is t equal to 1. So let's xt is equal to xt minus 1 minus the step size eta times gradient of fit xt minus 1. Up to this is just simple SGD. And the one bad point, one weak point of this simple SGD method is the variance. Basically, this random sampling of your index, the index function, index it, could generate high variance sigma square, and that can prevent your convergence trajectory to the optimal point, which can make some oscillation or some very bad behavior Okay, so to prevent this bad behavior, we have to introduce some auxiliary random variable or some random variable y that can reduce the variance, and also to prevent additional bias due to the y addition, we have to subtract the expectation of y as well, like the previous page. Okay, so the idea is, let's use the full batch gradient mu tilde and the x tilde. Okay, so every time use the same index it, we subtract the gradient of fit xt minus 1, the SGD, by the, again, the SGD vector, the same gradient fit, but with different function point. Here we do not use xt minus 1, but instead we use x tilde. Okay? And to remove the bias due to this additional subtraction, we have to add mu tilde. That is basically expectation of, that is equal to expectation of gradient of fit x tilde. Okay, so why this is useful? So when so here we have a starting point x tilde, and we update m times from x tilde. Okay, so this is x1, this is x2, this is x3, and so on. Okay, so if eta is sufficiently small, we can say that x tilde and xt quite close. And when f is smooth, we assume fi is beta smooth. So when f is smooth, we can say that the gradient of fit xt minus 1 and gradient of fit x tilde has very strong positive correlation. So we can expect that this additional operation, this simple trick, can reduce the variance while keeping the same expectation. Okay, that's why SVRG algorithm can very fastly converge to the solution, and even with the noise, the random gradient, we can converge to the solution. Okay, so this is theorem. Expectation of fx tilde s minus fx star. This is less than or equal to h to the s fx0 tilde, the initial point, minus fx star. So here h is equal to 1 over alpha times eta, the step size, 1 minus 2 beta eta times m plus 2 beta eta 1 minus 2 beta eta, which is strictly less than 1. We can make this by using sufficiently large m and sufficiently small eta step size. Okay.